learning. Okay. So when we talk about machine learning, I want to go back from some of the examples. I want to recall some of the very important events happened in the past 10 years. Um, Hopefully you guys still remember this news. But I do need to double check because this was 10 years ago. And you guys were in maybe middle school, elementary school. Anyone still remember this? What happened here? Not much. Yeah, a little bit. Okay. Yeah, we talked maybe 4 years ago. Most of our students will know this very well. Yeah, because you guys were a little bit young. Anyway, just a short story. Okay, so this was the event happened in 2016. There was a company called DeepMind. Right now, DeepMind has been bought or acquired by Google. It's a part of Google, but it's a British company and then very small company, but they got a very smart guys there. And they did build this program called AlphaGo. It's a program that plays Go, and then they claim this is really good, so they set up some games with this world champion from Korea. And then they played for maybe 5, 6 games. You can find the record. I think that the computer lost 2 games and won 4 games. Basically, the computer dominated the whole competition. And then one of the last game from what I saw was it was a very like simple bug, a very like a big mistake. It's obviously there was something wrong with the program, like a very bad move, and then they lost it. But most of the time, the computer was dominating the world champion. Okay, so that's what happened, and obviously it's a very good program, very smart program. But I want to give you some kind of background. Okay, back in 2016 or 17, around that period of time, when this thing happens, um, it was a very, very big news. I remember, normally around the end of the year, like a New Year's Day, different media start to summarize like the top 10 biggest news in the previous year, the top 10, whatever, right? You can see this news in most of those lists, okay, in terms of like a biggest breakthroughs, biggest news, biggest surprise, whatever you call it. This was a very, very big deal. Okay, but essentially it's just a program that it looks like it's just to play games and it doesn't sound that new. My question here is why this was such a big deal at that time. Because think about it, you guys play games all the time, right? Whenever you play games, you will play with a computer, right? Yeah, obviously the computer you can choose the difficulty. The computer sometimes is more intelligent. It's okay. It's not really that uncommon, and this one is just a Go game. Why this is such a big deal? Yeah. I think you guys can probably more or less feel it. It looks, probably feels the game a little bit different, right? But obviously, anyone actually play Go? No, yeah. So that's not that popular. But uh, from weekends, I don't play that either. Okay, but you can probably feel the game is not an easy game. Okay, that's why all these people is probably like similar to chess, right? So all these smart people are playing this, and probably the program is just very advanced. Okay, let me explain this one to you. But first of all, this was a very, very big deal. Honestly, the reason we spend so much efforts into AI, all those things, this event actually served a very important milestone. Honestly, before this event, there wasn't much discussion about AI. So between, let's say, 2010 to 2015, 2016, that 5, 6 years, I was very active in the industry. Around 2010, 11, I was a smartphone. As the iPhone became very popular around 2010, I was iPhone 4. You guys probably don't remember those. iPhone 4 and iPhone 4S is getting really good. And everyone started trying to switch their phone to smartphones. Okay. And then people started talk about building apps. And after that, people talk about cloud computing. Um, that's a very big term at that time. Nowadays, you heard about the cloud all the time, but they really became popular around 2011, 2012. And then some other things that's very popular during that period of time. People talk about Internet of Things, proposed by Google, like all these smart devices. They think everything should be connected to the internet. Everything should produce data. So there were a lot of different technology people talk about, but none of us mentioned about AI. At that time, people talk about AI, we still think AI is very, most of the time very stupid. It's not really useful at all. It's really after this event, okay, people really all of a sudden realize, wow, AI can be this good today. And that actually triggers a lot of more work and research in this field, which also contributed to the AI we see today. So only within the 10 years. Let me give you some kind of more insights on why this is a very big deal. To understand that, okay, I want to show you this example first. Um, so in fact, that program to play chat Go wasn't really like a new thing. A long time ago, we had this program to play chess. Okay. Actually, I do remember this one very well. So this thing happens in 1997. Okay. So there is a program called Deep Blue. This program is made by IBM. And then they also set up the same thing to play with the world champion from Russia. And as you can see, this guy, he doesn't play. Okay. He's just, reading from the computer and make the move. Then this is the world champion. Uh, 1997, I was sixth grade. I was back in China. I actually still remember when I go back to home at lunch break, I actually watched the TV news. This was also one of the news from my memory. Okay. So it was, think about it, I actually saw this one back from China. And that basically means this one was also a very, very big deal. Okay. Otherwise, we're not going to see this kind of things in some of the major media. It's just a program. Okay. But what happened at that time, I think the Deep Blue also dominated the whole game. They won maybe two, three games totally. I like the guy, the champion was very frustrated. Okay. Because they just can't believe the computer can be that good. Okay. And with this story, I also want you to think about it. Uh, you know, if this one we already did it back in 1997. Okay, now in 2016, 20 years later, you build another program to play Go. And I still told you that this is a very big deal in 2017, 19, sorry, 16. Why? I mean, since we already saw this before, right? This one was already pretty good. Why you talk about that one? It's still that good. And then what if next day I build another AI to play another game? Are you still going to claim that as a very big true? Um, in other words, let me ask you this. If in 1997 we can already build a very smart program like this, and why do we have to wait for 20 years to build another similar program to play Go? Any thoughts? How many of you play chess? No? Right. Yep. I mean, you can probably assume the answer is that probably Go is not as easy as this one. It's probably more complicated. All right. Even though we don't play, it's hard to compare, but from this, I think for sure it's not because the humans are not interested in playing goals and they don't want to build it. Um, the truth is obviously the goal is more difficult to build. That kind of program is more harder, okay, to implement. Okay. But you can probably see and feel all of this. But let me give you a very concrete estimation on why this one is more difficult, how much more difficult. Okay. To understand this one, it's very easy. Let's come back to a simpler game, okay? Because the chess and the Go are a little bit hard to estimate. Now, if you think about tic-tac-toe, okay, so this one, everyone know how it works. This is a lot easier to explain. Okay. Let's assume that we are trying to build a program. Okay, if some of you probably done this program, okay, to do a tic-tac-toe game, maybe in a terminal. Okay, so I want you to write a program that you can let a user to play with a computer. So you do the terminal input, and then the most important part about this code is that you build a computer player that can place and interact with the human player. Okay, this is human versus computer. I know most of you probably done like a human versus human. You do two input, right? You take turns. That's easy, and all you need to do is check the winning conditions. But think about how can you build a program that can also play for you with you. Okay, so that's the thing we're trying to build. Now you got to think about the algorithms. Okay, so let's design this algorithm a little bit. I'm going to do a very simple simulation here. So let's say the humans start the first move. Okay, so they put this into the center. All right. Now, if you're trying to build a program, now you need to think about the algorithms. Okay. Tell me what is your algorithm to decide how do you make the next move? So I play the first one here, and you don't need to tell me the code. Okay, just your algorithm. How would you design your algorithm to make the next move?
They have it just like check for open spaces
Yeah.
nearby.
Okay.
That would be the first one. And then it's check to see if, let's say for example, the person playing is using X's.
Okay.
If they have like two X's in a row, um, they go for a blocking maneuver first versus an attack maneuver.
All right. Okay, very good. Okay, so it's a very clear pseudocode. Okay, so first check the openness, right? And then you also mentioned that you want to make sure that the other guy is not winning, or if you can win, right? If you have some two already in a row. Okay, but let's say this situation. Okay, nobody's winning. You got plenty of openness, and then which spot are you gonna choose?
I feel like going for a diagonal approach usually wins.
Diagonal, right? So you want to touch the corners first,
Yeah,
right? Okay, well that's your algorithm. Very good, very good. Any other ideas? This could be a easy like interview questions. Okay, you got to be more active on this. Uh, yes.
Have it try and predict the next move, what you're gonna make based on your first move. So instead of blocking it, just outright win.
Yeah. So you're saying that we're trying to predict based on the current board, right? What the player is gonna go next, right? And then you're gonna block or prevent some of the good boards. Okay, very good. Well, that's a lot more sophisticated. You're gonna try to predict the next one. Okay, very good. But neither of these two solutions is the perfect solution because think about the corner approach. That is really based on your experiences. I agree that this game is very easy. I do agree. Maybe the corner is better. Maybe you can prove it. But if we never prove it, it's just your feeling. Okay. You're never gonna know if this is true or not. Especially if we go to the more complex game, there it's very hard to get those experience unless you are the world champion. And then the prediction approach, that's also good, but that prediction sounds very hard. Okay, so if you're not predicting things accurately, and then you're not gonna make the best move. Can we get a really good and optimized move? Yes.
Is there like some sort of formula?
Yeah, that's similar to the first approach. We're assuming there's some kind of patterns, right? Formula that summarize the situation. Maybe yes, but that's probably our question. So how do you get that kind of a formula?
Definitely feel like some machine learning where I have like a bunch of players play tic-tac-toe
Uh-huh.
and then kind of
Yeah.
based on where someone puts the first dot, like the percentage of where someone's gonna put the other dot.
Yeah.
I feel like that.
Yeah, well, that's the very advanced approach. Okay, well, I think first of all, for this one, we may not have that many, gameplays or history data, but also I think this game is very easy, right? So maybe we don't need to learn that much. That's actually what they did for the goal. Okay, we'll talk about that one later, but let's not talk about machine learning for this one. It's probably too much for a simple game like this. Simpler, any simple solutions, but that works really well. Yes. Okay. Random could be a good one, but is there a way you can do better than random? Because random doesn't guarantee the best solution. In some of the problem, the random could be a very important step. Okay, you will see that in the machine learning algorithm sometimes. But in this case, you don't need to risk to do the random. There should be a better way to do this. In other words, it shouldn't be too hard for you guys to build a program to guarantee the best move. How would you guarantee it's the best move? Don't overcomplicate it, okay? Nothing to do with machine learning, nothing to do with prediction. Just use the simplest way. What is the simplest way? If you're given an algorithm question, what is a naive simplest way to use first? Yeah, exactly. Okay, so to summarize, just do a brute force. Can we try that? Right? So I would just try every single move to evaluate which one is better. Remember, when you are doing the interview questions, okay, most of the question does involve a little bit of algorithm. But during the interview, very often it's very stressful. Sometimes you just all of a sudden your brain becomes blank. Okay, you can't think about anything. You don't want to be silent, stuck there. That doesn't look very good. If you know that you're not going to come up with a good solution or very efficient solution shortly, start with the naive approach, brute force. Okay, use loops, nested loops to try every single solution to see if that works. Okay, that process, at least first of all, you can take some time, as fill up the time so that you can have the conversation going. And also, as you're going through that solution, it gives you more time to think about a more optimized solution. Okay, it's better than telling you nothing. Anytime if you don't know the solution, start with the brute force. In this case, let's start from brute force. Instead of randomly picking the spot, I'm going to think about try every single one and to see which one is better. Okay, so this is what I'm going to do. Since I know your move, I will know that for my turn, I have all of these 8 possibility or options. Okay, I can go here, and obviously we can go here. All right, I'm going to not read all of this. Okay, so I can also go here. So we talked that there are a total of 8 possibilities. So in your memory, okay, you can place the things in each one of the spot and you use your condition to check if I have a winning or if I have a losing, right? So obviously in this case, nobody's winning or losing. Okay. So what should we do? We can keep simulating it, right? I'm gonna say, oh, if I do go to here, I can't see who is winning, but let me see what the other player is gonna do. Now, some of you mentioned about predicting the move. In this case, you don't have to predict. You just need to evaluate and try every single possibility. Because then I will know, okay, so if you go here, okay, and what we're gonna do next is that, okay, so the player will have total of 7 options. The player can go to here. The humans can go to here. And obviously the humans can go to other places like here. All right. So And I will look at, okay, if that's the case, does any cases will make the human player win? And if yes, we will know that this is going to be a very bad move because if you do there, and the human player could possibly win. And then they will tell you that you will know that this shouldn't be the one choice for you to use, right? But obviously you still cannot see it. So what you do is you keep analyzing or keep simulating the situation for every single possibility. That's why one of you mentioned about decision tree. Eventually, if I draw this whole thing, it's going to be a very giant tree to cover every single case. Now, think about at the bottom part, okay? Or we call it leaves, right? So the board is going to be filled up, okay? Very likely going to be something like this. Something like this, okay? It's going to be something like this, or maybe I do a winning case. All right, it's going to be filled up. So let's say after the first move, and our program started simulating every single possibility, every single move. It takes some time. I'm going to generate all these leaves. If I have that whole tree, what I can do is I can do some counting. I'm going to count, if I go to here, how many of those boards gave me a winning, how many of those gave me a losing, how many gave me a tie. Okay, so you will know the statistics. All right, you will know, well, this one gave me 30% of winning. Well, this one gave me 35% of winning. And in that case, I'm going to pick the highest. I'll make that move. All right. Simulation plus brute force. Does that make sense? Yeah. Naive approach, but it works best. For sure, this is going to be better than you do some kind of formula, some patterns, some rules, some experiences. You predict the next move. Those are way too overcomplicated. This one is going to be enough. And the best part is that you know you're going to get the best move. Okay, it's guaranteed. Because when the game starts, you already saw all the possibilities. Okay. So this is the best algorithm. Now, obviously, you can see how it works, but you might be start wondering, okay, this doesn't sound like a very efficient solution, right? Whenever we talk about brute force, loops, nested loops, we were told to analyze the time complexity. Is this efficient? Is this efficient in terms of time? Is this efficient in terms of space, right? So is that going to work? Can our computer handle this? Okay. Let me ask you this. If you write your code to do this type of approach for tic-tac-toe, does your computer can handle this easily? Your regular laptops, can your laptop handle this easily or not so easy? Probably, right? But you gotta know how to analyze this. Okay, let me ask you this. So this is what I would do. Because obviously this is gonna take a lot of space in memory. Okay, because you gotta save all this board, then you can do all this accounting stuff. So to estimate the complexity, you might want to look at the space first. Think about in this level, in memory, okay, you save this board. And as you are simulating for the next move, okay, you're going to generate at least 8 boards here because there are 8 possibilities. Okay. What about here? In this level, if I'm going to draw all the possibility for the next move, for all the whole level, how many boards are we going to generate? Just this level here. So that's the first move. This is the level where we're predicting the next human's move. If I generate all the possibility, how many total boards? Yes. How do you get it? Yeah, right? Because there are total 8 solutions here, and every board, if you draw the tree, there will be 7 more options. Okay. So the question is at the bottom part, how many? All the way to the bottom. How many boards you're going to generate in total? Just that one level. Okay. How many? Yes. Very good. Yep. Pretty simple, right? So you every level, and then this, because every one of this will have six. We're gonna time six, and then at the bottom level you're gonna all the way from 1 to 8. All right. So if we estimate the whole thing, you can ignore the previous one. Wow, this one even has AI here. I never seen this. Okay. Anyway, it doesn't count anymore. Okay, so this is very cool. Okay, this one I never seen this one before. I don't know when they added the feature, but that's the answer. Okay, so 40,000. So you're gonna do 40,000 boards saved in your memory, and you can then estimate. Okay, every board takes I think 1 byte, maybe 2 bytes should be enough. So this one is just about like you can probably call it 80K, right? That much of a space. 80 KB, that's just piece of cake for any computer. Okay, even 20 years ago. I don't know what's your if you remember the specs of your very first computer. How much memory did you get? Your first one, not the current one. The current one, I think you all have 8 GB, probably 8 to 16 GB at least. Short, smaller one, maybe 4. But your first computer, how much memory? Do you remember? Anyone?
4 GB.
4 GB? That's pretty good.
Yeah.
Okay. Anyone, any others? Yes.
I think I got like 1 or 2 gigabytes. It was like a really, really old computer
Yeah,
from like
yeah.
2006.
Exactly. Okay. My first computer was 4 MB. Okay. Back in 1995. Okay. And then quickly we updated to 8 MB. Megabytes. Okay. So at that time, the reason you guys in the 2400 you learn the time complexity, and then honestly another important thing was the space complexity. That's the thing we're talking about here. These days you don't look at the space anymore because space is so cheap. Okay. But 25 years ago, because the memory only has 8 MB, and then the operating system going to take the majority chunk of it, and the space left for your program is really, really limited. It's sometimes hundreds of 600 kilobytes. So when you're running games, a lot of time we got to do a lot of cleaning of the memory. We stop a lot of program and then reboot the computer. We do those things. So we have to show from the command line how much memory is left, and every game has very specific requirements. If you're not meeting that number, you can't really start your game from the command line. So the programmers actually were very, very smart at that time. They try to, optimize a lot of things to make sure they fit the memory requirements. But nowadays, the memory is no longer an issue. Okay. However, back here, okay, 80 KB, even 20, 30 years ago, you can still save it pretty easily. Not a big deal. So this is a piece of cake. All right. So, but I hope you can understand brute force as a very effective approach. They use space for exchange. The the optimization. Okay, the guaranteed best solution. Okay, very good. You don't really need to over engineering this one to use machine learning or anything else. Okay. Now, if you understand this one, guys, this is very important. We're gonna go back to here. Okay. Obviously, you never saw any news on TikTok Toe game because that's very simple program. Everyone can write it pretty easily. Now, this is obviously it's not a program most people can write, and IBM did it, and then they did it so well, 25 years ago, almost 30 years ago. Let's estimate in the same way. If we are going to use, for example, brute force, okay, and you're also going to generate all these possibilities of the boards. How many are you going to generate for chess? And obviously, this is very hard to estimate, okay, but let's simplify the program. All you can think about is using the same approach here, okay, because the chess has a lot of things with dealing with different, different ways of movements, the rules. Let's forget about those. Let's just look at the boards. How big is the chess board? chessboard. How big? How many spots? 64, right? Yeah. 8 by 8. Okay, so let's simplify it. Just use the tic-tac-toe approach to estimate if you draw this whole thing, okay, all the way at the bottom, that row, how many? You're gonna generate for this one? Same, right? Factorial. Oh, 34 factorial. Okay. How much is this? Use your calculator to do it first. I don't know if the PowerPoint can show it. Give me a quick number.
One point two six eight eight to the 89th power.
Okay, 89 power, basically like 89 zeros, almost 90 zeros. Okay. Yeah. Oh, wow, this is pretty good. Okay, this is a new thing happened. Okay, very good. Okay, it saved us a lot of efforts. So pretty big number. Let me ask you this. Does your computer can hold this? Yeah, very difficult. Yeah, it's pretty challenging. Okay, you even use a really optimized way, to condense the story. I mean, the representation of the board. I think this is too much for a personal computer to handle. Okay, even today. Well, but people built it back in 30 years ago. All right. What kind of how did they implement this? Did they use the brute force? No? Actually, they did. Okay, so they did use the brute force. That's why that guy is so frustrated. There's no way he can win. Okay, but then how? Well, if you remember, I told you, it was IBM who built this program. Okay, I don't know how much you know about IBM, their strengths. The company is not going very well these days. But, 30, 40, 50 years ago, it was probably um, really, really important company. Okay. Um, they're really good at making the big computers, the supercomputers, and big system, operating systems. Personal computer, you all use Windows. But if you look at the servers, the large computers, and many years ago, they all use the things from IBM. There is a OS 360, something like this. I never use that. I only read some of the articles about those. So IBM was a very, very important player in the industry. Okay, for both operating systems and also the computers. But they make big computers. They also have a personal computers. Some of you maybe have the IBM, the what's that? ThinkPad, right? What is that? ThinkPad? The IBM laptop. Yeah, I think it's ThinkPad. But then in early 2000, they sold the whole personal computer to Lenovo. They don't run those anymore, but the brand is still there. The brand was very strong, so they keep using it. Um, and then IBM started to do transfer to all their business to the software solutions. They make like a system, like if you go to some of the retail stores, you do the checkout, they print the receipt. A lot of those machines, 10 years ago, a lot of those from IBM, because they found those softwares makes more money. Because you just write a code and you resell that, and they pay the subscription monthly fees. It was better than just selling the computers. Okay, so they changed a lot of our business. But nowadays, I think I don't even know what they're doing. Okay, they had some kind of AI program, some cloud computing. I don't know who is using it, and yeah, it's not a very good company to be in. But at that time, they were very good. Okay, but how do they handle that big number, the 89 zeros? The answer was that they have supercomputers. Okay, they don't use personal computers. We just put together more computer. This is not a real image, okay, but this is just demonstration. Okay, they use super computers that can have a huge super memory. Obviously, I don't think they handle that many. Okay, 89 zero, that's still too many. They probably do a lot of optimization. Okay, we can cut different things and just to lower it because a lot of those you don't have to simulate all the way, right? So a lot of optimization is going on. So that was what happened. All right. Now, if you understand this, hopefully you can see, all right, now we look at this one, why we think this is a very big deal. All right. So what is the number here for Go? What's the size of the board for Go? Since you guys don't play, it's 19 by 19. Okay. 361. So what is the factorial of 361? This one need to be challenging. I want you to calculate first. Can you find a calculator to give me the results? Some calculator doesn't work for this. So how many zeros? 768. Okay. Yeah, see, this one cannot give me the answer. Yeah, this one doesn't. But I remember it's something about like 700 zeros. Okay. Something at that level. 700. Okay, zeros. All right. So if you do the brute force for Go, okay, it's going to be very effective, but you need that much memory. Could IBM handle it? No, obviously not, because they didn't build it. Even using supercomputers, this is still too much. They can't do enough optimization to hold 700, whatever we call that big number, that many boards. Okay, not to mention the board is bigger, so you actually, it does cost more to save one board than the chess. Okay, so that's why people stuck here. Okay, they got very excited about solving this problem, but they found out this one is not going to work. And we waited for so long, okay, 20 years later, and then we finally built a program to do it. And obviously, it's not because we got a better computers, it's because we got a better algorithms. Okay, they realize that if you do the brute force, even though it's very effective, but it's just not efficient to build. We have to rethink about the game. That's when they apply for machine learning. Okay, the approach they use is exactly as one of you just mentioned. Okay, we don't try every single thing. We learn from the past. We learn from the history. So we collect all this game histories as much as we can from all the professional players. We look at every single step. We look at the sequence. We look at results, and we try to let computer to read all of this and summarize some of the very effective rules and lessons. And then they put all the rules and lessons into a model and use that model to direct, okay, how we're going to make every single move based on the situation, based on the input. And that process is called machine learning. And it's the same kind of idea as we showed earlier about large language model. Okay, we'll give you data, we'll give you history, you learn it. Once you finish learning, then you play, you try, you handle the new input and tell me the answer. It turned out this one works really well. Okay, that's when people realize, wow, machine learning can be this good. Okay, and honestly, from this event, a lot of researchers, a lot of companies start to go back to look at all this machine learning stuff to rebuild a lot of things. Machine learning was never a new topic. I think some of the initial machine learning algorithm came in the 70s, 80s, 90s. Next time we're gonna talk about some very basic algorithm. I think a lot of those came long time ago. But the reason that machine learning never took off was because we didn't have enough data. We didn't have enough meaningful data. And this example actually brought a very new angle to let people to rethink about, oh, actually, if you get this much data on this type of problems, the machine learning can actually go really beyond your expectation. Okay. But it happens 2016. Also, there are some reasons. Okay, first of all, at this time, you have to admit that the computers and resources storage is getting better. personal computer cannot handle this one, but we have a servers. We have a cloud computing. Using the server is so simple. And then also, after 2010, as I mentioned, we have mobile, people use more internet, we generate more data. And when we have more data, there are more things we can do with this data to do machine learning. That's why in 80s, 90s, the machine learning never going to be useful because there's not really much data. There's not even enough computer for people to use. It doesn't generate anything. Okay, so a lot of things put together, and this one happens. All right. So that's machine learning. I want to stop here today. Next time we're going to dive into how exactly do we design and run the machine learning problem. Okay. We also want to show you how do you use very simple libraries to run those. Okay. So we're going to do a lot of Python, and then the most important library is called sklearn or scikit-learn, this one. All right. So if you're interested, you can take a look at this one. And this is like the most classical library to run machine learning. They have a lot of algorithms. But this one doesn't involve too much about deep learning, like neural networks. Okay, that one is using some different libraries. But the idea is the same. We want you to look at this one first because this one really shows the initial uh, algorithms or ideas behind also machine learning. Okay, once you understand this one, if you go to the neural networks or deep learning algorithms, it will probably start to make more sense. Okay, so I think we'll come back on Thursday. I will wrap up the very basic machine learning with scikit-learn. Okay, but from today, it's just a very quick discussion overview. Okay, understand two things: how the large language model works, predict the next word, and the way we build those learning model is to use machine learning on a large data set. Okay, machine learning, the history, why it's so powerful today, what the important factors you need to have in order to build these machine learning models are data and algorithms. All right, so let's stop here. Okay, we'll come back on Thursday and I'll dive into the technical things then. All right. So I'll try to get all the things recorded. Okay, I'll also put those into YouTube if you want to look at that later.